Hello everyone, welcome to the 10th lecture. Well, maybe the 11th. Last time we discussed these project sessions, so I'm not counting that one. That actually raises a point. I noticed that there was a little bit of confusion about whether there were going to be lectures now that we had these individual projects handed out. I suppose in that regard what I should really say is that it's not like the lectures are here to help you do the projects, right? It's almost the other way around. The projects are here so that you can understand the lectures from a new perspective. And in that sense, all the projects that we did in the beginning, the first 4, were sort of there to build up the core knowledge, right? We saw different small order reduction techniques. And now that we've built up that core knowledge, we can actually address some more advanced topics. And that's precisely what we'll be doing for pretty much the rest of the series of the class during these lectures. And so we're going to be talking about some more advanced things that we can only talk about now that we understand the basics. So to kind of point that out, let's take a look at the syllabus. This was in the introductory lecture, and this is what we said we were going to talk about. And I sort of divided it into 3 parts, where part 1 was about the fundamentals and the mathematical background, part 2 was where we started looking at really the reduced basis methods, and now we're pretty much headed towards part 3, right, the advanced concepts. Yeah, so to address it a little bit more specifically, I see that my video is kind of overlaying some of the points, but I think it's clear. So in the introductory lecture we saw the motivation of these methods, which we've also readdressed and rehearsed throughout the series. Then we talked about some traditional engineering approaches where we saw static condensation and model decomposition. And then we talked about the foundations of parameterized partial differential equations, where we talked about the Kolmogorov n-width, the smoothness of these manifolds, and we really tried to answer the question, is a reduced basis method at all possible? And I think that was emphasized as well throughout this lecture series, was this division between an offline and online strategy. Yeah, so these are all 3 points that we've talked about. Now that we understood at that point the parameterized partial differential equations, and we understood the real objective of what we want to achieve with reduced basis methods, we started looking at a couple of examples of such methods, right? Then we saw proper orthogonal decomposition, and where we had these snapshot matrices, where the affine decomposition became very important. Then we had the sampling strategies in POD. Then we also talked about the greedy method, the greedy basis generation strategy, and we talked about error estimates, both in the offline and in the online stages. And that's roughly where we stopped last time, which means that we still have about 4 points here in this list, and there's going to be 4 lectures, so I'll address 1 point per lecture, effectively. And what we're going to talk about today is this one. So we're going to talk about what we're going to do if our problem is no longer affinely decomposable. And the solution strategy for that is this empirical interpolation. And there's also going to be 2 flavors of that, so that's what we'll see today. Now that means that we sort of skipped over one of the reduced basis methods, the proper generalized decomposition. I'll actually get back to that all the way towards the end, so that to wrap things up, I think that one becomes particularly interesting after we've discussed a couple of these more advanced topics, and specifically actually the nonlinear part. Okay, so what we're going to deal with today is problems that are non-affine. Why is that important or challenging? Here again we have our online-offline decomposition, and throughout this general outline, this general strategy, we find that the affine decomposition pops up everywhere. Yeah? You see it here in the generation of our offline, either snapshots or with the greedy method. Yeah? To make that not extremely expensive, we need some sort of affine decomposability, else we would have to reassemble our complete stiffness matrix, mass matrix, and force vector in every new parameter point, which might already be prohibitively expensive, given that we're dealing with these high fidelity systems of equations. So that's sort of in combination with this one. After that, we're pre-computing these components that we're then going to use during the offline phase, right? During the online phase. So these also heavily depend on there being some sort of affine decomposability. Only due to that can we do this effectively. Now then we even needed this in the computation of the error estimates. which also means that we also need that during the online stage. So in the practical outline of what we're doing, we see that this pops up everywhere. On top of that, we also saw this a couple of times in the theoretical background. Also for the error estimations, that we assumed that the stability constant can be obtained from these different affine components. We also assumed an affine decomposability in the derivation of the manifold smoothness. Right? So both in the theory and in the practice, this is very, very important. And what that really means is that even in the case where a problem is not really affinely decomposable, we're still going to force it to be. Just to be clear? Yeah, okay. Then I'll switch over to my notes. So firstly, I would like to make a list of where we exactly see this affine decomposability. So where have we assumed this? Go full screen. Yes. So we have assumed affine decomposability. Decomposition. We have assumed the affine decomposition at the following points for our bilinear form. Right? We have a parameter-dependent bilinear form, which means that we have a bilinear form which takes a function u and a function v and a parameter mu, which may be some sort of a set of a whole bunch of numbers. And we're going to assume that we can write that as the sum of over QB components of functions dependent on mu multiplied by bilinear forms independent of mu. Right? So that's the affine decomposition assumption. But we didn't only assume this necessarily for the bilinear form, also for the linear form, which would be our right hand side, that's where our forcing would be, which also is assumed to be, in a general sense, assumed to be dependent on the parameter. And we also assumed that to be in an affine sense. And the last thing, which we have not really talked much about, but which still fits in this list, is that also our output functional can have a parameter dependence. And if it does, then we also assume that it behaves in an affine way. Yeah, and the output functional was really the one value that we might be interested in from a complete computation, which could be the drag in aerodynamic computations, maybe a total strain energy in solid mechanics, or a displacement at a certain point, or a load at a certain point. And that would be the output functional, which again we assume to be dependent as such. Yeah, so suppose that our parameter dependence is, well, exactly the stiffness of the material, and we're interested in the total strain energy in the system. Well, then clearly the parameter shows up in S, and it would need to be in this affine way. And we required this affine decomposition also for a number of reasons. So which was required? For, first of all, the theoretical background. And specifically during our talks about the Kolmogorov n-width, which said something about how wide our solution manifold was, in the sense that if it was very wide, then it would be very difficult to approximate it with a finite dimensional small subset of bases. And whereas if it was very thin, then we could be very effective at trying to approximate all the solution states with a small number of bases. And we required this for the manifold smoothness. Which was about, even though maybe the Kolmogorov n-width is very, very small, so we can theoretically approximate a complete solution manifold with just a few bases, how effective will our finite element framework be able to do that, as opposed to be highly dependent on small variations. Then, during the offline stage, we had this step where we want to explore the solution manifold, so the manifold exploration during the offline stage. So either through POD or with greedy, right? We're scanning our manifold, creating a reduced basis in some sense. Then perhaps most importantly, we need this affine decomposability for quick assembly in the offline phase. Sorry, the online phase. So during operations, yeah, that's really kind of the most important point here. If we do not have that, then assembling our finite element matrices for the reduced order model during the online phase will be prohibitively expensive. It will kind of invalidate the whole process. And lastly, still to also address this for the error estimation. Both during online and during offline. Okay, so clearly this is important, and it is also typically not the case, really, even though we have assumed this. And a couple of you will also find this to be true during your project sessions, the ones that we're doing right now, so the individual projects. Yeah, so for instance, if we're talking about transient loading, which I think shows up in 2 projects, if we do not want to do this extremely simplistically, then we would have some sort of we would have either a parameter dependence on there, or at the very least, certainly not an affine decomposition in that sense. Yeah? At each time step, our load might be completely different. For the geometric variability, the way that that's going to show up, it also doesn't really satisfy this affine decomposition, especially if we're going to look at deformations that are slightly more complex than standard stretching. And anyone that's working with any form of output functional also probably doesn't have this affine decomposition in this clean sense. And so also during individual projects, this is actually not always satisfied. So we need a strategy for handling that if that tends not to be the case. So let's write this in the particular example of linear elasticity. So, but what if? So what if a bilinear form, which now becomes vector to vectors, which is the integral over our domain of the symmetric gradient of u, double contracted with our stiffness tensor. And suppose now that this stiffness tensor has a position dependence as well as a material dependence. Now we have seen cases where the stiffness tensor was position dependent, right? We had these different blocks in our material. But we could still separate that into each of the different blocks and still write it as this sum. That's what we've done in the project so far. But suppose now that C is a highly complex function, right? So just to clarify, in our project so far we've looked at this bracket, and then we separated it into sort of these 3 squares, and in each square we would have a different material. And in that sense we can still separate it, right? We can separate this integral into these 3 squares. But suppose now that this C might look something like this. Might be a function that looks something like this, which might be the result of some sort of mixing parameters in the way that this material is generated. And depending on different parameters in our mixing strategy, we might get different mixing patterns. So then clearly we can't just separate this into different blocks, and even more so we can't really separate this at all in this affine sense. So how would we handle something like that? Okay, let's take a look at another example, slightly easier maybe, that still illustrates all the points. For a linear form, I suppose that, sticking with the example of linear elasticity, we might have a boundary contribution of a certain traction, and suppose that that traction is material of parameter dependent. Yeah, so we might exactly be interested in adding a different load and see how the structure responds to that. And that might be a very feasible engineering example. And that load might look very complex, and it might certainly not look like something that you can pull apart into different components. And the same thing holds for a body force. Suppose that body force is also position dependent, and that position dependence also changes on the parameter. Which would also be a very relevant case, that you're interested in how your structure responds to different loadings, and that's exactly what we're interested in some of the individual projects. So how would we go about handling this case? So what we really want to do, and I'll focus really on this term because that illustrates everything of importance. So we need to represent, somehow we need to represent both these terms, and really also the bilinear form, as some finite sum. And the way that we're going to do that is not by splitting up that integral directly into a finite sum of integrals, but we're going to focus on these spatial dependent functions. So I'm going to, instead of splitting directly the linear form, I'm going to split this function f into different components. Yeah, so I'm going to take the function f, which is parameter and space dependent, and I'm going to approximate this as a sum until n of coefficients which are parameter dependent times new functions which are just spatially dependent. Is this a valid assumption? Well, actually this is something that we've seen many times in engineering. Right? A Fourier series kind of looks like this. Polynomial series expansion kind of looks like this. So this is certainly something that is theoretically possible. Then becomes the question, how effective is this? And actually we'll find that doing a Fourier sum is not the most effective way, because a function might look nothing like a sine or a cosine, so you would have to add many modes in order to make it look like one. So we're going to do this differently, and we're going to actually make use of the way that f looks like. So we're going to use information about f. And that kind of makes this an empirical process, and that's also the E in DEIM, yeah? Empirical interpolation. But I'm kind of skipping ahead of myself. What happens if we make this assumption of this spatially dependent function f? If I substitute this assumption, then we find that that component of the linear form looks like this. Yeah, so our original part was this. And this would now be approximated by a sum over m of coefficients that depend on mu. I can pull those out of the integral, right? They're independent of space, of the integral over our domain, times these new functions hi, which are only dependent on space and independent of the parameter point, dotted with v. So I think I'll start dropping the underbars. In the case of linear elasticity, clearly these are vector fields, but I'll be more general, so I'll stop underlining these. This can be any kind of can be scalar, vector, tensor. And what we see, if we make that assumption of our function f, then and we substitute that, then we find something that satisfies this affine decomposability. Now this kind of again looks like something of this form. Okay, so that's the general strategy, and clearly this hinges on the design and the way that we would obtain the C's and the H's. And as I said, there's a couple of clear examples that we know from calculus, a series expansion of polynomials and a Fourier series. But we're going to do this empirically by making use of known information of the function f. And that's what the empirical interpolation method is about. So, discrete, we'll keep that in between brackets because that's the second method, but really first we're going to look at the empirical interpolation method. And so the questions that we have left are, firstly, how to obtain those functions. So how to obtain hi of x, and secondly, how to obtain our coefficient functions, which are now functions of mu. So suppose that we have some form of functions h for some method. Then we might naturally think of the coefficients as, well, those weightings that give it the best approximation to f. Well, what's going to be the best approximation? Well, we could use some sort of norm, right? We could use maybe in a least square sense, or an L2 norm, or some other kind of norm, or a maximal deviation, that would be an L infinity norm actually. But all those kind of processes are quite expensive, and that's really a key thing here. We want to be able to do this with as little expense as possible. And specifically, we want to be able to do this during the online phase. And during the online phase, well, we really don't want to have to obtain this f as a field everywhere, right? That's an expensive procedure. So we want to somehow do this with as few queries to our function f as possible. But that's only after we know our functions h. And how would we know that these functions h? Well, really there's two strategies of doing something like this, and that's exactly where the d comes from or does not come from. And that is in a greedy sense. And if we do that, then we get the empirical interpolation method, or in a POD sense. And then we get discrete empirical interpolation. So that's funny, right? Why do these terms that we know from a reduced basis method now suddenly show up in this application as well, even though it doesn't really seem much like what we're doing so far? And that's really because this is pretty much exactly what we've been doing so far, right? We're trying to approximate some function of space by a finite sum of only a few representative bases. And then we're trying to find that in such a way that these bases can approximate our true function f as effectively as possible for the whole range of parameter dependence. Right? So this is pretty much exactly what we've been doing. And in that sense, we also obtain that we can do this with precisely these two methods, greedy and POD. Okay, so I'll explain in a minute what that then would look like. What would a greedy method look like for obtaining these functions h, and what would a POD method look like for obtaining h. But first I want to talk about these coefficients c. And again, we want to do this cheaply. So I'm first going to assume that by some approach we obtained our functions h. Now how do we obtain a function c of mu? And as I said, our preference is not viable. Our preference will be to have a best approximation in that basis for our function f. But that's going to be too expensive, and that's not a process that we really want to do during our online phase. What we want to do is to do this in as minimal as possible evaluations of f, and then we go into the field of interpolation. So somehow we want to design a sort of an interpolation process that defines these coefficients. And then I only need to interpolate at a couple of points, and I would have as many evaluations of f as I have bases, and that's it, right? So I only need to evaluate it only a handful of times, and that I'll be able to do cheaply. So I'm first going to talk a little bit more about 2 and then I'll get back to 1. And again, to summarize what I said before is that in the best case scenario, we would want to obtain those C's such that F is best approximated by, well, that's sum over C and H's. And again, best, we typically measure that in some form of norm. However, that is not something we can do. That's going to be too expensive. So instead, we focus, or let me say it like this, we force an interpolatory property on our basis H. We force an interpolatory property on our basis Hi, which are functions of space. So what does that mean? Well, interpolation property is really that if I evaluate my approximation at a handful of points, well then that's going to give me the same value as evaluating the true function at those points. Yeah? So my approximation is equal to the true function at a handful of points. If I only have one basis, then in principle I'm only able to claim this for one point. If I have two bases, 2 degrees of freedom, then I can set them to be equal to that other function at 2 locations. And in general, what this requires is that our approximation has a bunch of coefficients which are mu dependent multiplied by our basis is going to be equal to our function, which is also mu dependent, at a handful of locations. And these locations are the interpolation points, xj. And in literature, we actually call these points magic points. So this is a true term. So for how many points can we make this claim? Well, as many as we have bases, right? We can make this claim on as many points as we have degrees of freedom. So we can do this for j is equal to 1 until m. Now this is sort of a system of equations, and we can write it as such. So that leaves, or that gives a system of equations namely B, a matrix times the vector C is equal to a vector F, where the entries of B, I think this has to be Ji, is equal to these guys, Hi, Xj. And again, these interpolation points, the locations in space where we force this property, they're given. They're set, we have to decide those, but they're fixed for every parameter point, for every subsequent addition of bases. So those are the coefficients in the matrix B. Then the vector C, the values in the vector C are, well, exactly the Ci's from here. Right, so Ci, maybe I should write this, which are mu dependent. And our vector F consists of the evaluation of our function f at these magic points. Now, after I've in some way created a basis h with which I want to approximate the function f, and I've specified the interpolation points, the magic points, then the entries of the matrix B, so the Bij's, are going to be fixed. Right? They'll be fixed irrespective of the parameter, because the parameter dependence is in the right-hand side and thereby also in the C. But the B matrix is fixed, which means that in a priori sense I can already invert that matrix, and now I have a direct method of obtaining my coefficients C, which are parameter dependent, from a matrix multiplication of a known matrix B multiplied by a parameter dependent vector f, and a parameter dependent vector is simply obtained by evaluating the true function f at a couple of locations, these magic point locations. So this is in a general sense what interpolation is, and I don't know, this might be a little bit confusing because it might not actually look like what you're familiar with interpolation. What we might be familiar with in terms of interpolation is that we have some functions that are 1 at some location and 0 at other locations, and those are just special cases of these functions h, right? If I have my functions to have that interpolation property, is what we call that, then they are, well, what is that property exactly? The property is that at the magic points, we either have a 1 for one of the bases and a 0 for all other bases. And if we have that property, so if our basis H satisfies that property, then the matrix B here is the identity matrix. It will be 1 at the magic point associated with that basis, and it will be 0 with the magic points associated to all the other bases. So we get the identity matrix. Yeah? B will be the identity, which means that the inverse of B is also the identity matrix, which means that the coefficients associated to these bases is simply the identity times, well, that f vector, and that f vectors consists of the values of the function at those magic points. Yeah, so that's a more direct, that's maybe a more familiar approach to interpolation, that we simply set certain functions to be equal to the value of the function at that location. But that's only possible because the basis is interpolatory, meaning that it's 1 at one magic point and 0 at all other magic points. Yeah, so this is in a more general sense what interpolation is about, if we have functions that, basis functions that do not satisfy that property. Yeah, so this is a more general story. Okay, now we started off not knowing what h was, and by the end of this story we have another question, because what magic points to choose, right? And actually the effectiveness of a method like this depends a lot on these magic points. So we now have a new question. But what are these special interpolatory magic points? And the answer to that is that it now depends on our method for constructing or for obtaining this basis hx. Which was really the first question that I stated here to begin with. So we'll start talking about that now. And as I also said back then, we really have two approaches of doing this, or two strategies that have become standardized. And that was the greedy strategy and the POD strategy. And I'm first going to talk about the greedy approach. And then this whole story is called the empirical interpolation method. Now I can really summarize this, the whole strategy by a relatively short sentence. What we're going to do in the greedy method of empirical interpolation is we're going to add a function hx to our set, to the set, And this function is going to be, so as the error field that introduces the highest peak error. Now what does that mean? So this is again iterative procedure, right? So let me readdress what was greedy again. Greedy is a strategy for trying to solve a minimization process in an iterative way, where in each iteration we're trying to solve a new simplified local optimization strategy. Yeah? So we see here, well, it is iterative because we're going to add hx step by step. And it is a local optimization process because it's trying to add precisely that function that introduces the highest peak error. And it's doing that with respect to the previous knowledge, yeah? Because at any new function that we might add, we have our previous functions, and this error field is then the result if we would use our interpolation strategy with the previous basis. Yeah? So suppose that we have four bases, four functions h, then I would add the fifth one by looking at all points in my parameter space. Yeah? So I'm going to go over all these mu's. I will obtain the true function f, and I will obtain my approximation in our interpolation strategy sense. And then I'll find the mu, the parameter point, for which the error that I'm making with my method so far is largest. And that is exactly the function as the error itself that I will add to my method. Now what does that mean? That means in the next step, at that given mu, I'll be able to make a zero error, right? Because the error that I was making previously, I can now represent that in a new space. Yeah, so what you'll see in greedy is we're adding functions step by step in very much the same way that we also add functions to our reduced basis method by a local optimization as that point that introduces the worst approximation. And I'll show you what this looks like in just a second. First I also have to address this question, right? What are these magic points now? And the way that we propose this for EIM is that the magic points x, j, and p are the locations of the peak errors. Now this is a choice. It is also a pretty intuitive choice, right? We have certain error fields, and now we're going to interpolate them in such a way that at least what was priorly the worst error, that is set to 0. Because now we're setting our approximation equal to that function at the magic point. Yeah? So where we first had our peak error, we now ensure that in every new iteration we will have a 0 error. Okay, so this might still sound a little vague. Here I have the method written as an algorithm, and after this I'll actually show you an example. So let me rehearse. The input for our empirical interpolation method is, well, a maximum number of bases that we might want to add, or an error tolerance. And the output is going to be a set of basis functions, so these are now rows in my notation, they're mu's, and interpolation points, so these are the magic points, x, j. So that's going to be the output, right? That's what we need for our interpolation method. And the algorithm then is as follows. First we initialize, we set m to 0, we have well, some e naught that's going to be larger than our error tolerance to make sure that we don't break our algorithm in the first step. And in the first step, the interpolation of our function g, which in my notation was the f, is going to be set to 0. And the parameter point mu, where we will add our first basis, is going to be the parameter point where our approximation for G, well right now we don't have any approximation, so it's just going to be G itself, is going to be maximum. Okay, after that we're going to go in a while loop, and we're going to keep on going through that while loop until we satisfy our error tolerance threshold, or we hit the maximum number of bases that we want to add. And what we're going to do is we're going to take the error, so in this place is a residual, but it's really the error, of the function minus our approximation. Right? That's our error field. Then the new magic point is going to be the point where the error in an absolute sense is maximum. And then there's sort of a normalization step. Then, as an input for the next while loop, we have, well, first of all, our new maximum error, right? And we can see if this new maximum error is going to be larger than or smaller than our tolerance to see if we will break or not. And a new parameter point. And the way that we obtain this is by going over all possible mu's, taking our true function, subtracting our approximation, and seeing what the maximum error is. That's the L infinity norm. That's the point at which the error is maximum. So we'll do this for every mu, which gives us, well, a new maximum error, right? If we do this for every single mu, then we know well, we have a complete range of errors, and EM is then the maximum. And the mu for which corresponds to that maximum error is also stored for the next iteration. Because in the next iteration, we are going to add precisely again that error field to our bases at again the point where this error was maximum. Yeah, so it's iterative, and each iteration is trying to find a solution to this local optimization property. Okay, maybe still a bit vague, so let's take a look at an example. So here we have an example of a function f which might be spatial dependent and parameter dependent. Now, what does this function look like? Well, certainly it's rather complex. I would say it consists of three components. Right? We have here this exponential, then we have another exponential, and we have here sort of a linear multiplied by a quadratic function of space. Now, these all kind of look like e to the power minus r square. This guy also. So that's sort of a Gaussian curve. And then we have here our mu dependence, and we have, oh, this should also be mu, sorry. Yeah, we have a mu dependence there, and we have a mu dependence here. So what does that look like? So I'm plotting this here for a bunch of different mu's, right? A bunch of different parameters. So our parameter space right now is one-dimensional, right? I only have a scalar function as a parameter. And we see that this first exponential is sort of depicted here. The second one is the one that's over here. And as we improve or increase our mu, there's a couple of things happening. Well, firstly, that first exponential is multiplied by our mu, which means that it becomes larger and larger in magnitude, right? That's why this becomes so bright towards the end. And the second thing that is happening is that the parameter dependence of this guy is going to shift our Gaussian well or distribution to the left, right? So this is slowly wandering to the left. And then lastly, we have also this multiplication with mu of our additional function, which is sort of creating that field as well, on top of this. Yeah, so all I really want to illustrate by this is a complex function where the function of space depends on the parameter mu, and clearly not in a way that we can normally separate into a bunch of, or into the series expansion, because that's what we want to achieve. Okay, so now we're going to use our greedy algorithm, or the EIM method, or EI method. And the first thing that we're going to do, right, we have an initialization phase. At this point, our approximation is simply 0. We don't have an approximation. So we're going to add the function. We're going to add the function that has the highest error field, or the highest peak error in its error field. Well, if I look at my solutions here for a whole bunch of mu's, then I find, well, clearly the highest peak value is the one associated to this mu over here. And that's exactly what I'll add as my first basis for this expansion process. Yeah, so this function, this basis, is precisely the one that you see for mu is equal to 7. So this actually corresponds to mu is equal to 7. So now we have obtained our first h, right? This is h1, which is a spatially dependent function, but independent of the parameter. Oh, that's a little too fast. Now the second thing that we needed in our algorithm was this interpolation point, this magic point. And we defined our magic point to be the location of that peak error. Yeah, so clearly if this is our error field compared to 0, then the point of the peak error, so our new magic point, will be right at the center, right? And that's what we're seeing here as well. So this all follows from the algorithm. Now if I use this basis and I try to approximate this function using our interpolation process, then I find that I'm making these errors still. Yeah, and the way that our greedy algorithm then works is that it's going to scan all these functions as for the different mu's. It's going to find the function that makes the largest error, and it will use that error field as an additional basis. And that's what we're seeing here. Yeah, so if I look at my functions here, then I say, well, clearly the one that has the largest error is going to be this guy, where the largest error is at this point. And that guy is precisely the second basis that we're adding. So that's basis number 2. Now don't get confused by the change in color. That's a sign flip due to the normalization process. If we look at the algorithm here, then also the way that I implemented this is you're dividing again by the largest error. I actually don't think that's necessary, but that's setting the value to 1. That kind of simplifies a little bit what the B matrix in the end looks like. But I would say it's not very important. Okay, so this is the second function that's also added to our basis. By the way, what we're seeing now is that our greedy method consists now of, well, first one solution, and that's the solution at this location. Which means that I'm perfectly able to interpolate that original function, which means that the error here is equal to 0. And that was also the case already here. So I have a 0 error. Here I still had errors everywhere else, but now I'm adding the error field from this guy, which means that, well, I can also represent precisely that function now, and again, I also have a 0 error when I try to represent that function. Yeah, so this was corresponding to mu is equal to 7, this is the error field when mu is equal to 0, and this was h1, this is h2. And we continue with this process, and what we already can see is that the magnitude of the error decreases. Well, first of all, we see that there's relatively little error towards the end, towards mu has a large value, but still a large error when mu is small. And when we add the second basis, then this all changes. You can see this. But clearly now I'm sort of missing the information from the center. And what the greedy algorithm will do is we'll add the error field that corresponds to, well, the largest error field, which would roughly be now this mu is equal to 4, with a new interpolation point, a magic point, as again the location of the maximum error. So I'm going to add this basis as my third basis to the series expansion. Yeah, so that's that basis. Yeah, that's the same guy. But again, yellow and blue are flipped due to the normalization process. And now I can see that I can perfectly represent this guy, I can perfectly represent this guy, I can also perfectly represent that guy. And the error of all the ones in between is starting to drop further and further. Now I can keep on doing this, and at each stage that I'm doing that, I can store the maximum error that I'm making for all possible mu's, and I would get a convergence curve that looks kind of like this. Yeah, so this was the first basis that we added, and I see I still make an error, a maximum error of roughly 1. Well, that was actually precisely this guy. That's a roughly value of 1. Then I add another basis, and the maximum error that I make, so that was here. Wait, sorry, I'm going in the wrong direction. The maximum error that I make was here is still roughly 1, right? That's why it has dropped so little. And after I add 3 bases, it starts to drop a little bit more, and I have a maximum error of, I would say, 0.98. Yeah, but so that's going pretty slow, but we find that after a few of these iterations, we suddenly start to drop in error very considerably. And after we add roughly 10 of these bases in this method, we have an error that is, I think, 0.2% or something like that. Now that means that even though, just to be clear, even though we only have one parameter, mu, which is a scalar value, ranges from 0 to 7 in my example, even though we have only one parameter dependence, if we would use this interpolation approach, this empirical interpolation approach, our series expansion for our linear form or wherever would consist of 10 sums. Or if we're happy with an error of 1%, well, then still 9 or 8 or whatever, right? So that's kind of to illustrate also that there's not a direct connection between the amount of parameters that we have in our parameter space and the amount of components in our sum. Which was the case for each of the projects, but that was just by example. Okay, so this is the empirical interpolation method based on a greedy algorithm. Now, what was the other approach to doing this? That was a principal orthogonal decomposition approach. And if we do that, then we get a discrete exterior interpolation method. Just one thing that I would still like to clarify, even though I'm only showing this for 8 graphs, I'm doing this for all kinds of values in between. So I think I actually used, in the greedy algorithm, I'm scanning over 300 points in between 0 and 7. So the fact that we end up getting bases 1, 2, and 3, which correspond to locations 0, 7, and 4 is sort of coincidental. Yeah? But also this maximum error does not relate to these graphs. It's in between the entire range from 0 to 7, right? Else after 7 bases I'll be able to represent everything. Okay. And that kind of becomes a little bit important to appreciate the difference between greedy and POD. So in POD what we're going to do is we're going to add hx, a new basis, to the set. Oh wait, sorry. That's the wrong page here. I was going to say, that doesn't sound anything like POD. So the way that we're describing this is we're going to fill a snapshot matrix with solutions of our function fx at different mu locations. And we're going to use POD or SVD to determine the most important modes. So in greedy what we're doing is we're adding to our set of interpolation functions h, our bases, sort of really the solution fields, right? Or in this case the error fields. So it's a linear dependence, so you can also say we're adding solution fields, just like we did for greedy in the reduced basis method. And POD was different. POD is adding a whole bunch of possible solutions to a matrix and using this linear algebra to find the most important contributions to the complete set, right? So in that sense, POD is able to give bases that in a more global sense are optimal for this problem. Yep. So the greedy is optimal for specific locations in a parameter set, and POD is trying to generalize that a little bit. Now for greedy we had a very clear idea of where the magic points will be. Those are the points of highest error. So how do we obtain the magic points for this guy? Well, it's slightly more complex, but in the same basic idea. So now the magic points x, j, and p are the locations of maximal error again when when the J basis is approximated in interpolatory sense, so interpolated with the first until J minus 1 set of bases. So what does that mean? What we're going to do is reduce POD. That's something we're familiar with. From POD we obtain a bunch of basis functions, and we know from POD that the first ones are going to be the ones that that represent the complete set of solution states best. And then we're going to take the magic points to be those locations where each of the first few bases would make the largest error when they try to approximate a new basis. And what does that look like algorithmically? We create a snapshot matrix of possible solutions. We do an SVD, singular value decomposition, and we take the first n modes, or so many modes as to satisfy a certain error threshold. Well, in the initialization phase, because at that point our approximation is going to be 0, the point of maximum error is going to simply be the point at which our basis function is maximum. So the first point, the first magic point corresponding to the first basis function is simply the maximal value of that basis function. Then for every subsequent basis function, so from to the end, we're going to define, or we're going to obtain the error that we're making to approximate that nth, so the new basis function, by all the previous basis functions. So this is now, again, I don't know why they changed notation, but this was before the interpolation for the, well, maybe n minus 1. So the interpolation of the new basis function on the n minus 1 set of bases. That's going to be the error that we're making if we're trying to represent a new basis by all previous bases. And then we're defining our new magic point as the location where that error is maximum. Okay, what does that look like? Same example, same function. Again, mu dependent. A couple of components. So the spatial dependence changes as mu changes. Then I'm doing a POD, so I'm generating, I think I generated 20 snapshots from 0 to 7. I'm putting those in a matrix. So I think I have like a 20 by 40 matrix, 20 by 400 matrix. I think these are 20 by 20 points. So it makes 400 points per solution state and then 20 snapshots. After that I'm performing SVD, singular value decomposition. And if I only take the first mode, then this is going to be the basis. Yeah? So this is the first mode of the SVD. This is the function that is the most important if we're trying to approximate all other functions in the set. The magic point is the point where that function is maximal, right? So that's right now just the center again. And here we see that if I were only to use that single function to try and approximate all these solutions, then I'm still making these errors. Yeah, and in a sense we see that this is already a little better than what our previous method used, the greedy method, because the greedy method was really able to handle the one specific function where mu was equal to 7, and it kind of messed up everything else, or it didn't improve anything else really. And this one is doing a little better. But still it fails to take into account the first few. So let's see what happens after we add a second basis. That's the second basis. And if we use those to try and approximate all our possible solutions, then we're still making the errors that you're seeing right here. So different from the greedy method, no error field is 0, right? That's simply not what this method is trying to do. That was what the greedy method was trying to do. But rather what this POD approach is it's trying to reduce the error overall, right? So there's no single mu for which the error is precisely 0, but we're trying to minimize the error in a general sense. And after I have my third basis, I get something like this. Then I can keep on doing this for more and more bases, and you get a convergence curve that looks something like this. Now interestingly, the final error that we're making is roughly an order of magnitude smaller. And I would say that follows based on what we know from this method, right? It tries to approximate or tries to reduce the error in a general sense as opposed to very specific locations, so it can be more effective. Okay, now if we compare these two, then we see here the first few bases with the first few magic points, either for the greedy approach or with the POD approach, and we get the convergence curve on the right. And so in a sense they kind of look similar, even though the bases look very different. It's also interesting to see that the first basis is still quite the same. After that it starts to deviate. But the convergence is, in terms of shape, quite similar. And anything else I would say really depends on the situation, right? So I can try and make claims from graphs like these, but it would be very situationally dependent. And actually I think that one of the projects is also about this, like how well do these methods work for particular classes of problems. Okay, I think that's actually everything that I had in mind for today. So this lecture is a little bit shorter. I think that's also going to be the case for the subsequent lectures. I don't think the most appropriate way of proceeding is giving full 1.5 hour lectures on these advanced topics. So I'll try to keep them a little bit more succinct, more narrow and focused. So my objective here is not that you know precisely all the details of how these methods work. I want to emphasize that there are still gaps in the reduced basis approach that we've talked about so far. In this case, the gap or the flaw was that we assumed this affine decomposability, which really doesn't happen in most cases. Then I want to illustrate, or I want to emphasize that there are solution strategies to that. And I'll try to give you a bit of a feel for a theoretical background, to give you an idea of what these methods work like under the hood. And I'll try to also illustrate some practice to give you more of an intuitive feel of what this does, right? But other than that, I don't think it's my strategy here should be to have you know every single detail of these methods. If you need these for the project or for whatever kind of work you might do later, then well, that is the time to figure out the details, but maybe not necessarily now. Okay, so well, the things that we're still going to be talking about in the next few lectures are geometry as a variable, nonlinear problems, right, both in terms of solid mechanics and fluid mechanics, and then the last reduced basis method that we haven't talked about yet. So it means I'll still be giving live lectures every Thursday, and during the Tuesday project sessions we'll keep the same strategy. I kind of like the way that the big blue button system works, so I think we'll stick with that. And I haven't still quite figured out how I want to do the final grading strategy. As I've explained to some of you, the way that we did that last year was with a presentation, and I quite like that because then everybody gets to see what other people are doing, right? We can learn from each other's experience. I'm not sure if due to Corona that's the way we should proceed this year as well, so I'm still making up my mind about that. Okay, then thank you for your attention, and I'll talk to you on Tuesday.